Today's lesson, transformations of logarithmic functions. So much of this is going to be familiar from previous transformation lessons. So I hope that most of this is sort of a review to you. But we'll start off with just talking about the basic, what a log function looks like. And then once we have that base function down, the rest of the transformations will kick in. Some retro transformers coming up here for your transformation lesson. Okay, graphing logarithmic functions. The easiest way to deal with graphing logarithmic functions is to remember they're inverses of exponentials. So log graphs are very mysterious when you first look at them because it's a new base function. We haven't had a new base function in a little while, and so it's kind of awkward when you first run into a new base function. But if you remember it's an inverse of an exponential function, it's fairly straightforward to come up with its graph. So in your mind, reverse the roles of x and y for the exponential function, and the graph of logarithmic function comes easy. Well, comes easier. I don't know if it's easy the first time you go through it. Okay, for example, consider the graph of y equals log base 10 of x, which is the inverse of y equals 10 to the x. So when you're first learning and it says graph y equals log base 10 of x, if you're having any trouble at all, instead picture what y equals 10 to the x looks like, and then reverse the roles of x and y. For instance, we know that y equals 10 to the x has a y-intercept of 1. When you sub in x equals 0 into 10 to the x, you get 10 to the power of 0, which is 1. So that means the x-intercept of log base 10 will be 1. Next, we know that f at x goes to 0 as x goes to negative infinity. As you look on the left side of a 10 to the x graph, and I brought one up on the screen here. I've loaded up Desmos here, which is a free app you can get and also a website. And the red graph is the 10 to the x graph. And you can see as we go to x values going large and negative, negative 1, 2, 3, 4, 5, the 10 to the x graph heads towards 0. And that's what that PowerPoint was trying to say right there. Next, what that means is the function for log will go to negative infinity as x goes to 0. Those two things reverse each other. See, the y-axis becomes the asymptote instead of the x-axis becoming the asymptote. So you can see now the y-axis is the asymptote. And this thing goes towards the asymptote for large negative y values instead of large negative x values, as it did with the 10 to the x graph. And now, as far as the other side of end behavior, as x goes to infinity for a 10 to the x graph, the function goes to infinity, but very, very quickly. It takes off, the y values take off very quickly, which means when you look at it the other way, the x values are going to take off very quickly. So let's look at that. You see the red graph, the y values take off very quickly, but in the blue graph, that y equals 10 to the x graph, it's the x values that take off very quickly. Also, the coordinates of y equals log base 10 at x are the reverse of the coordinates of y equals 10 to the x. I'll just show you a couple of points by what I mean by that. See, on this graph, you have 0, 1. So on this graph, you have 1, 0. On this graph, you have 1, 10 right there. Up there, about 1, 10 there. You know, I can't get it right on the point there. 1, 10. There it is, 1, 10. And then so on the inverse graph, you get the point 10, 1 right there. Okay, so you can reverse points as well. Not as useful because it goes off to infinity so fast, but it can be a help when you're graphing log base functions to use individual points. You want to get a couple on your page there, but a couple of points might be enough to point you in the right direction. So as we have done with several other functions, we can apply transformations to the graph of log functions. So sketch the graph of y equals negative 2 log base 10 of x minus 4. And then it says state the domain and range at the end. Well, there's three transformations I see in this function. Is that we're going to have to vertically stretch it by factor 2. We're going to have to vertically reflect it, and we're going to have to move it right 4. Hopefully, all of that is stuff that you're like, oh yeah, I remember all that stuff. And so when I start off with my basic log base 10 graph, and I know many of you like to do these with a table of values, and you're more than welcome to do that. If you're good at that SRT thing on your table of values, yes, you can do it that way. I'm just showing the graphs. You can visualize what's happening here. And I've added an extra point here. 32, 1.5 is a nice extra point that I put in there to use as a reference point. But again, 2 reference points really should be enough. So what am I going to do first to this thing? I'm going to do the vertical reflection, and watch carefully. It's going to happen. It's going to actually vertically reflect on the screen so you can see it happen. Here it goes, and there's a vertical reflection. So the point 10, 1 became 10, negative 1, and that point 32, 1.5 became 32, negative 1.5. If you're doing SRT, you'll see those things happen on your table. Then it says a vertical stretch factor 2. Here they go. All those y values are going to double. Watch carefully. Watch the screen. Here it comes. There, all those y values doubled. Again, you'll see that happen in your table of values if you're doing this with SRT. And then finally move the whole thing right 4. Here it comes. The asymptote moves over right 4. And so we get a new graph and all the x values. We've added 4 onto them. Pretty straightforward stuff as long as you can get the log base graph. You may choose to do it all in one step, but be careful if you're doing it all in one step. Again, I think most of you are SRT people, and so you do all those things right in your table of values. So domain, now we can look at the domain. Now that we have the graph, we see the x values have to be greater than 4, and we see the y values can be anything. This thing stretches off to infinity in both directions. One more example where we'll do it the opposite way around. It says the graph of a logarithmic function, y equals log base 5 of x, has been vertically compressed by factor 2/3. So I'm thinking about vertical compression of 2/3. Okay, that's going to be a multiple out front of this thing. Horizontally stretched by a factor of 4. So if I want a horizontal stretch of 4, I'm going to need a 1/4 inside the brackets. And reflected in the y-axis, that's a horizontal reflection, so I'm going to need a negative inside. And then what else? Vertical asymptote is now -2, so it's been moved left 2, and then 3 units down. And again, I really hope that your that's all pretty straightforward stuff, that you're sort of used to transformations. If not, you got to review your transformations because we've been doing a lot of that stuff. And so you get this equation. There's the 2/3 out front. There's the negative in front for the horizontal reflection, the 1/4 for the horizontal stretch, and then left 2 and down 3. Left 2 because now the vertical asymptote's at -2 instead of at 0 like it is with the normal log graph. Here, take a look at the normal log graph here. I'll turn off the red one and just have the blue one. See, it's got its asymptote at 0. So if the asymptote's been moved over to -2, this thing must have been moved left 2. State its domain and range. Oh, now hang on a second here. It could be you can just look at an equation and get domain and range. But most of us, we need the graph, at least in our head or a quick sketch of it. So I'm going to go over to Desmos, and I might have to go back and forth a minute if I can't remember all this. So what was it? Y equals 2/5. So 2/5. And then arrow over. And I think it was log base 5. So I got to go into the functions here and find log. There's log base whatever I want. So I want log base 5. And I think it was moved left 2, so I think it's an x plus 2. I'll go back and check that to be sure in just a second. And I forget the vertical translation, so I got to look. Oh, I forgot the -1/4 too, and a -3 at the end. Okay, good thing I looked. -3 at the end, and inside the brackets, okay, I'm going to need another set of brackets here at some point. Let's go -1 divided by 4, see if I get that. Yeah, that works good. And then I need a bracket around the x plus 2. It already wants me to do the other bracket. It knows what it's doing there, so that's good. And so now I've got a picture of the graph there that really helps me to do domain and range. You see, it's all left of -2. If you try to do that in your head without trying a quick sketch, you could easily make a mistake. So left of -2, and the y values go to infinity either way. So less than -2 is what I'm looking for on the domain, and the range is y element or reals. Okay, so really a nice review of transformations in this lesson. Make the effort to go through and get used to graphing a couple different log graphs. If you wanted to do log base 5, I encourage you to graph 5 to the x first, make a little table of values with 5 to the x, and then just flip the values, the x and y values, the 0.01